Hello, good afternoon. My name is Oshan Roberts, and I'd like to welcome you all to the final of series, or final of the first series, final six supply chain events as part of the Tiger Project today, hosted by EMEC and facilitated by myself as the Business Development Manager for Minesto. I will just run through some key housekeeping aspects before we really get started. Again, thank you for joining the event. The webinar is being recorded and it's going to be made available through the Tiger website, which you can see there on YouTube after the live event. I also think that the slides will be available on the website as well. There's going to be a Q&A session at the end, so you can ask your questions to all the panelists. Please, if you can use the Q&A function to post your questions, you'll see it at the bottom as part of your view, and you can also upload those upvote, I should say, those questions if you're interested in hearing the answer. And for sort of any technical issues, could you please use the chat function, and somebody working in the background will kind of have a look at that and help you out. For the agenda today, I will start with a quick overview and intro to Tiger. We have a fantastic expert panel today. We've got David Collier, Chief Operating Officer for Minesto, Darren Hayes, Technical Director of Dublin Offshore, Erwan Nicholas, Head of Research and Development for Sabella, and Adam Leonard-Williams, who's a Marine Operations Consultant for James Fisher. There'll be a Q&A session, like I said, and then we'll summarize and close around about 2:30 or 3:30 if you're in Europe. So quick overview of Tiger. What is Tiger? Well, Tiger stands for Tidal Stream Industry Energizer Project, and it's a 45.4 million euro project sponsored by the Interreg Channel France program. And it's a 4-year project with 18 partners, which was approved in July 2019. And it's there to sort of build cross-border partnerships to develop new technologies, to test and demonstrate them at a number of locations across the Channel region. And this learning is going to be used to sort of make a stronger case for developing and commercializing the tidal stream energy industry between France and the UK, and hopefully expand into across the globe. Now, what is Tiger? You'll see Tiger there. We've mentioned the 18 partners. This is the Tiger area. We've got 6 technology developers and sub-projects, 6 universities and 2 regional agencies. You can see the sort of active sites where we'll be deploying the technology as part of Tiger, with the little wave logo in each of the areas there. And that green area you'll see highlighted, or the dark green area, are the sort of regions that would be eligible for funding as part of this Interreg program. And Tiger, of course, is led by OREC, the Offshore Renewable Energy Catapults, and they themselves are sort of based in the UK, in Cornwall, and as part of the sort of catapult network, which looks to sort of fill the gap in the UK's innovation landscape. And it's true that in the UK, we have fantastic sort of businesses, world-leading sort of academic institutions, but really the sort of catapult network has been brought together to sort of fill that gap between bringing that learning from academia into industry to sort of support the delivery of new technology into the market and to drive economic growth. Now, what is Tiger about? I'll kind of flick through into this this slide, and we understand, of course, that the UK is world leading in terms of its marine energy technologies, but there's also this sort of policy gap that exists to enable the industry to move into being able to provide commercial projects. And there's a current lack of revenue support also in the UK and France, which is sort of detrimental to this progress for our industry. And we can see there from the OREC 2018 Wave and Tidal Cost Reduction Reports, if we look at the levelized cost of energy at 10 megawatts installed, bearing in mind this sort of variety of different turbines, different sites, and everyone's at a slightly different stage in development, it's there around sort of £300 per megawatt hour. And what Tiger wants to do, or should be doing, is sort of providing an evidence base and insights as to how we can bring that LCOE down. And it can do that if you look at the slide, the sort of three key areas, which is firstly the initial accelerated reduction, economies of volume, bulk order discounts, for example, the economies of scale, greater turbine ratings or improved turbine ratings, greater scale up in sites, and the accelerated learning that comes from that. The second part, the learning by doing and innovation, is there to sort of optimize the processes and products, whether it's connectors, and bring about learning by working in sort of real life operational conditions and to bring that sort of cost down. And the last part is to sort of bring down the cost of capital, de-risk that cost of capital by providing certification, by providing confidence to the investor market to bring that down. And if you couple these things with a sort of a learning rate, you'll see there that by the installation of gigawatts of capacity for our industry, we're looking to bring that cost of energy down to £80 per megawatt hour. And to do that, Tiger has this range of work packages, which is also sort of underpinned by the sort of knowledge transfer and the collaboration between technology developers and academia. So the first one, we're looking at sort of the learning by doing, which is work package 1, tidal energy site development and deployment in those respective areas I pointed out in the slide earlier. Second work package 2, sector and technology development, and bringing in these sort of innovation aspects to the sort of sector and working together with supply chain to provide that innovation and to improve component efficiency, process efficiency, and form clusters that can enable the development of our industry. Cost reduction analysis, where we'll bring us all that sort of learning together and form an evidence case to root in policy, which can act as a robust base to bring commercialization into the fore for our industry. We're looking to work with the supply chain, which is why we're here right now, specifically on the development of optimized components and processes. We're open to working across all organizations from across sectors. And I think the last thing to say is that, we would like to collaborate as part of Tiger. There's an opportunity to collaborate with all like-minded projects and associations. So if you want to get in touch, if you're looking to put yourself into the ring when it comes to this project, please have a look at the sort of contact details here. And I can show them at the end, and you will be able to put you in touch with whoever you need to speak to within the Tiger Consortium. And that's the last thing I have to say. So I just want to introduce my colleague, David Collier, which is the Chief Operating Officer for Minesto, to begin his presentation. Thank you.
Thanks, Ossian. So here I'm going to talk a little bit about how the supply chain can help us in terms of developing the tidal stream industry. As Ossian pointed out, it's key. It's a key two-way process between us and the supply chain. If the supply chain can do it better than we can, then we're going to use the supply chain. That's the rule of thumb. So this is what I'm trying to cover in the short time available in terms of generic headings. You can see I've taken quite a broad approach to offshore operations in terms of the supply chain, starting with developing concepts all the way through to installing systems and infrastructure, and then obviously going on to offshore O&M operations. So with no further ado, we'll step on through. I think the first thing to point out, which is probably known by most people, that this tidal stream is now a worldwide industry. Wherever there's high tidal flows or ocean currents, you'll probably find a tidal developer looking at it closely, and if not looking at it closely, actually trying to install tidal turbines in there to develop it. So in the case of Minesto, we have a number of projects around the world. Our headquarters from an operations point of view is in Holyhead in the UK. But we have currently a project in the Faroe Islands where I'm based right now. We have a small office in Taiwan where we're looking at the opportunities there. And obviously we've also got collaboration with partners in France and in North America for further demonstration projects. So it's worldwide, and the opportunities truly are also worldwide. The first thing I'd like to talk about is marine operations in the respect of design and support. Currently, tidal energy companies, development companies, are relatively small, sort of up to 100 people, and in most cases that doesn't give the opportunity to have a fully equipped full-time marine operations team, and so it's necessary to rely on the industry, the contracting industry, to provide that support in most cases. The key lessons learned here is to select your contractor very carefully. There is a lot of differences between installing in a tidal flow and what people do in the oil and gas industry. So there is some areas where it reads across quite well, and there's other areas where it doesn't read across very well at all. So the word of caution there is to look at the experience of the marine operations team, and I think you'll hear about that a little bit later on in this webinar. In terms of vessel supply, again, there's no purpose-built specific vessels currently available for the tidal energy industry. So we're reliant on vessels from other industries, mainly oil and gas and increasingly wind industry. The way that we deal with this in Minesto is that for every significant operation, we work with a broker. We provide the broker with a specification of our requirements. He goes out to the market. He knows the market better than we do, and he can identify what vessels are available, normally on the spot market. Comes back to us with a short list, and then works with us to do the final negotiations with the owner. That process, in our experience, works very well for both parties, and normally you can find the vessel that you want and a price that you can afford using this process. This process also works, we find, pretty well for smaller vessels, multicats, DP multicats, and so going forward we're looking to use the same process up to the point where we can afford to have our own vessels, which will come, but it's not today. So for those sort of vessels, towing installation, again, working with a broker is what we find is the best way. The key probably lessons learned from a procurement point of view is look very closely at the cost of actually mobilizing the vessels, because they can be as significant as the day rate. So be careful. It's not all about day rate, it's all about the combination of mobilization and day rate. When it comes to very small vessels, the type of vessels you want to use for personnel transport, there's a different situation, we find that it's much better to find a very local operator and maintain a good relations with that operator, because what we found in the past and going forward is that you need a lot of flexibility when it comes to personnel transport, both in terms of sometimes you don't know when you need it, and sometimes weather will get in the way of the operations you plan. So you need to work with a local person that can provide that level of flexibility and at a moment's notice either come and help you or at a moment's notice be put down because the weather's not significant. This is a picture of a small vessel that we use for transporting people to the buoy that we had in Holyhead Deep for a period of time. Moving the subject a little bit to development of tools, in particular in relation to offshore installation. A couple of years ago, we thought this was the best way to install kites, which was to lift it into the sea and lift it out of the sea, and we worked closely with marine contractors to develop this system for us. Learning by doing, as Oshin mentioned, is one of the key aspects of our industry, and we learned by doing this in the summer when it's flat calm, it's great, but as soon as there's a small swell or a little bit of wind, it's not so good. So we ended up changing the process from lifting to a towing process. So we're now towing to site. The process of this meant that we changed the method of installing the kite or connecting the kite to the tether from the deck of the vessel to the foundation, the point where the tether meets the foundation. So this then in turn created another opportunity, and the opportunity was then to develop a system whereby the connection to the foundation could be done with a fairly limited capability vessel. So it's all about reducing LCOE, as Oshin mentioned. So we want something that's quick, safe, and affordable, both in terms of the actual connection system and in terms of the vessel system. And again, here we worked very closely with a supply chain partner to develop this system that's now been tested and proven to be very successful. So it's not all about installation tools. There's other areas where working with the supply chain we found is the best way for us, and I can think of a few examples. Probably the best example is in the areas of consent, EIA consent, and environmental monitoring. In these cases, there's a lot of experience in the industry, and most of that experience is concentrated in a number of experienced consultants, and we use one of these consultants to work very closely with to develop all our consenting and monitoring going forward. Looking forward now, we are now in the situation where we are designing and developing arrays of kites, and this requires another set of skills and components, and both in terms of engineering arrays, installing arrays, providing the components. Here we believe, for example, that our connection points will be subsea, so we're looking at subsea hubs. There is clearly some read across from the offshore wind industry here, but there are also some significant differences. The main ones being we are going to have turbines probably much closer together than offshore wind, and so there's opportunities and differences in the way that we connect them together. And the most likely scenario is that we will not be connecting the infield cables together on a platform due to the high tidal flows and the visual impact effects. And so we're looking at subsea hubs. So we are looking to work again with the supply chain to help us develop systems and processes to make this both possible and cost effective. In terms of subsea hubs, that process has started. You're probably aware of a subsea hub that was recently installed by CMAC and Atlantis in the Maycomb field. So that is the beginning of the process, and that will continue till we get systems and components for all arrays. In terms of offshore equipment, onshore equipment, up to now, where demonstration projects are a small number of turbines, quite often, single cables to shore, then the onshore equipment can be housed quite easily in a container like we got here in the Faroes. Moving forwards, then this will not be sufficient. When we scale up, we'll need more equipment onshore and substations as well. So other electrical equipment needs to be engineered and contained and installed. Again, there's an big area for the supply chain to both help and supply equipment into these projects. Cable landing, always an interesting talking point. Two main ways of doing it: trenching, which we've done here in the Faroes, or doing an HDD. Both require some level of expertise and some level of local content, and again, opportunities for the local supply chain to assist in these matters. Finally, assembly and maintenance. In Monesto, we have built a purpose-built assembly hall in Holyhead, which will be used for assembling our kites going forward. Clearly, there's still issues with transporting them to the sites, and for operations and maintenance, we're not anticipating that we're going to bring everything back to Holyhead. So there is a requirement for local facilities wherever the projects are, and I think that will probably relate to most tidal energy projects. If everything's small, like we've got here with our DG100, that quite nicely fits inside a standard transportation container, and we can package it off and send it off and reassemble it on the quayside when we get there. But that is not necessarily the same for obviously larger components. So there's opportunities there, both in logistics, transportation, and assembly facilities. This can be something simple like a quayside at any port facilities. Here is where we're working in the Faroes. We just hired a quayside, made that available to us, and we've rented a small space in a local facility where we can get undercover to do small amounts of maintenance. That's sufficient for now, but it won't be sufficient for the future. The future probably looks a little bit something like this, where you've got infrastructure requirements, cables to be laid, and so you may be looking for a much larger heavy lift offshore quay. Again, opportunities locally for this, and opportunities to develop the concepts for how this works. So very quick whiz through supply chain opportunities. I hope that gives you a better understanding of what we had to develop and our needs and requirements. And I look forward to questions later on. And in the meantime, I'm going to pass you on to Darren Hayes from Dublin Offshore. Thank you very much.
Okay, good afternoon, everybody. Thank you, David. My name is Darren Hayes, and I'm Technical Director at Dublin Offshore. Very happy to speak to you all today and tell you some about the experience I've had working on various tidal sites across the world. So in terms of agenda, I'd like to first give a brief introduction to Dublin Offshore and to give an overview of some of the work we're doing at present. We'll then take a bit of a trip down memory lane and talk about some of the lessons learned from undertaking tidal projects in the English Channel sites. So Dublin Offshore was founded in 2018. As partners, we decided to combine our experience, which included project and product development across a wide range of marine technology, from fixed wind, tidal, and more recently, floating offshore wind. In particular, on this slide, I've highlighted where this experience has involved work in tidal sites off the Brittany and Normandy coasts, which dates back to 2011. Our mission as a company, I guess, is to make a contribution to the deployment of offshore renewables. We're very keen to use our experience in the development of marine technology, product design, engineering, and marine operations to try to help and solve some of these industry challenges. So just an example of the type of work we're doing at the minute, I'm going to quickly run you through this mooring component we're developing for marine renewable applications. As those involved with floating platforms will know, when the machines are operating in highly energetic sites, you generally require large mooring systems to keep the device within an allowable excursion area. Once the wind or the current starts to act on the rotor, the drag quickly tensions up the mooring line. When waves start to act on top of that background thrust, you get very high snatch loads in the mooring system, and these must be accounted for in the design to deal with the high forces and fatigue. So in March this year, we were successful in an application to the Carbon Trust Floating Wind Technology Acceleration Competition and received part funding for the development of our load reduction solution called the LRD. So the LRD shown here sits on the mooring line between the seabed and the surface and reacts passively to the waves. It uses a counterbalance of buoyancy and mass to reduce the peak loads in the mooring system by up to 70%. It'll also reduce the number of cycles, therefore increasing the fatigue life. So having developed the numerical models and the basis of design, we engaged early in the process with DNV and received a statement of feasibility for it in May. We then built a 1:60 scale prototype, which we tested at the Lear National Ocean Test Facility in Cork during the summer. So in this video, you can see how the LRD operates in the mooring line, and you can see how it reacts while it's subjected to some fairly aggressive North Atlantic conditions. So following on from that, we designed, built, and installed the quarter-scale prototype off the west coast of Ireland. So here you can see the device, which is currently under operation. As of today, we're 70% through our test program, and we're capturing a wide range of data from mooring loads, accelerations, and environmental conditions. And you can see some of the load data here, and you can see we were able to pick up Hurricane Epsilon as it passed through this week. So that's just a quick snapshot of our current activities. In this project, I guess we went from an idea to TRL7 in 7 months. The ability to achieve that has come from some of the experiences developing innovative marine technology, which we'll now rewind to. So the English Channel sites I've worked on are Paimpol Breha and Ras Blanchard. Paimpol is a test site, and here you have good currents, but relatively benign when compared with some of the big commercial opportunities such as Ras Blanchard or the Bay of Fundy. At these sites, peak annual speeds will exceed 10 knots, and daily peak speeds rarely go below 7 knots. I guess, as David alluded to, our starting point for this was coming from, general marine operations, the golden rule for cable lay and offshore construction: stay away from high tidal current speed areas. So to work on these sites, we had to solve some kind of fundamental challenges, and they'd have been, how do you lift a 1,000-ton foundation, which was required for stability of the turbine? How do you control your position when you've got a 20-meter structure submerged in the current beneath the vessel? How do you connect the turbines to the grid? And most importantly, how do you achieve all of this safely and repeatedly? So when it came to executing the project, I mean, you step back and you break the major requirements of the project into smaller work packages, as is normal. However, I guess one of the key things in defining the work packages was making sure that there was clear interfaces between them. So on a project of this scale, the first time the turbine sees the foundation or the assembly sees the barge, it's too late to find out that something doesn't fit or somebody thought somebody else was responsible for bringing a component to site. In this case, we use very detailed inspection and test plans, which outlined, clearly what the hold points were at each stage of a component fabrication, and what checks had to be done prior to the release of the component from that phase of the project. So a simple example here would be, the foundation doesn't leave the fabrication yard until the interface with the turbine has been measured and confirmed within tolerance. So looking at some of the marine aspects of the project, the installation vessel used in this case is a purpose-built heavy lift catamaran barge, which was certified by BV. It had a 1,000-ton lifting capacity using the combined lifting of 3 traction winches, which raised and lowered a subsea frame. The subsea frame had 3 hydraulically activated ball grab tools, which engaged with female receivers on the subsea foundation. And this allowed for kind of rapid and fail-safe connection to the barge. The barge preparation works here would have included general vessel maintenance, in addition to major upgrades such as the lifting system was fully replaced in 2015. And there was always project-specific upgrades, such as cable handling equipment or testing equipment. Key lesson here, I guess, was ensuring total readiness of the barge and confidence in the onboard systems for all the activities that needed to be performed on the tidal site. So prior to departure for operations, we'd undertake rigorous testing of the lifting system, positioning, deck equipment, to reduce the risks of being delayed once the barge got to site. Because not only was a cost issue, it was more important that we wanted to make sure everything worked as it should during a very tight tidal window. So the effort that went into planning marine operations of this scale was significant and usually involved several months of preparation for a first-time operation on a given project. In terms of the process, we'd start by producing general storyboards and put that to a wider group to get expert input, build on things that we had learned in previous operations. We'd also have risk-based workshops to discuss the proposal and always considering the what ifs, like what if we lose position at this critical stage? What if we run out of time? We'd carefully consider how long every activity takes and how it fit into the overall tidal window. So when selecting the tidal window, you'll have an upper and a lower tidal speed that you can work in. These are usually determined by either the station keeping ability of the vessel or the allowable drag on the lifting system. So the shortest time between the two most constraint events give you your tidal window. And in this particular case, it was roughly about 90 minutes. We always kept 20 minutes of that back in case we needed to abort at the latest time of the operation. So everything had to be done within that remaining time. It was very important, I guess, at this point to have key stakeholders brought into the process. This would have included the marine superintendent, the marine warranty surveyor, and the client. We'd then take away some of these draft plans and undertake the engineering and the analysis. So tools we'd have used here would be Orcaflex, CSAM, Proteus DS, other well-known packages. We'd also perform significant analysis on the environmental data that we captured on the site, such as, from the ADCPs or wave riders, to get a better understanding of the tidal regime, the sea states, and the general environmental conditions that we'd be up against. All this analysis then would allow us to layer detail onto the initial storyboards, which ultimately became the method statements. So yeah, I guess the outputs of the planning we performed, we'd have several key deliverables that needed to be fully approved, understood, and communicated prior to the operation being undertaken. The method statement would be the overall document, but behind this we'd have several other key documents such as the timing sheets. You can see a screenshot of some of them there. So on these sheets, every activity, the timing of the activity, and who was responsible was laid out. We'd then have the final risk assessment. And with that, we'd have a pre-prepared contingency plan should any of those risks materialize during the operation. So an example would be, we'd have exact instructions laid out on what to do if the winch lost power while the turbine was lowered. We needed these pre-planned, as there really wasn't a time to figure it out on the site, because ultimately we'd have to be out of the flow prior to the turn of the tide. Finally, another output could have been a recommendation for marine trials. So if there was an aspect of the operation that couldn't be solved with planning, discussion, and analysis, we'd often include a day of trials prior to the operation. So this might include mimicking the operation or a specific part of it in a more benign current prior to going out onto the actual site. When we spoke about lessons earlier, I guess we didn't just rely on human feedback to improve our understanding of the operation. Where possible, we collected and analysed data from the operations to make assessment against our initial analysis and calculations. Some examples here would have been the loads and the winches at various stages of the operation. So we'd inspect this data and we'd see, check it to see if maybe we could lower the turbine at an earlier point of the tidal cycle, or we'd analyze the dynamic amplification factors to see if we could increase the allowable sea state that we could work in. Another aspect we'd have looked at was kind of tow bridle tension. It gave us a better understanding of the amount of power we needed to maintain position, and compare that to the power that was available in the installation vessel. So the intent for all this analysis, I guess, was to open out the tidal windows and to increase the accessibility on the site to as high as possible. So just to conclude, I've listed some of the kind of key takeaways for you. The key takeaways from this, and it might be interesting in the future endeavours of those involved with the Tiger project. In terms of mobilisation, the area is very well served with really good ports in Brest or Cherbourg, really good water depths there and infrastructure. Crane capacity used to be an issue, but this is probably no longer the case because there's some very large offshore wind being mobilised from the area at the minute. In terms of marine operations, the key one is just good planning is essential. The sites are full of potential, as you all know, but they're also full of danger if you don't know what you're up against. So that's it from me. Thanks for your attention. Please feel free to get in touch if you'd like to discuss further. I'm now going to hand over to Erwin Nicola to hear about Sabella's offshore operations.
Thank you, Darren. So I'm Erwin Nicola from Sabella. I'm head of research and development department, and I will present you our feedbacks and emerging needs on offshore operations for seabed arrays. The summary of my presentation, we will first present Sabella's company, our technology, our D10 project, presentation and feedbacks, the emerging needs, and the main project and procurement opportunities. First, is a company working on seabed tidal turbines, and we installed our first one in 2008, which was a small one, and was the first tidal turbine installed in France. And the second one is a bigger one, the D10 machine, 10-meter diameter and 1 megawatt power, installed in 2015. It was the first tidal turbine to supply electricity to French grid. Sabla was created in 2008. We are 25 employees. We work on engineering, procurement, construction, and installation of tidal turbines. A turnover around 1 million, and shareholding structure composed of industrials, financials, founders, and also management. Sabela has cutting-edge technology for a differentiated solution. We use a horizontal axis turbine with fixed symmetrical blades and no yaw system. This was to improve yield, proven design and roughness, so that we don't have a weak system on the turbine. We have a low rotation speed, a direct drive generator with permanent magnet, so we don't have gearbox, and we avoid by that way wearing parts. We have also an onboard conversion chain and a transformation with complete redundancy. The fact is we integrate directly the conversion system so that we can provide a stabilized power, stabilized on frequency and voltage at the end of the turbine. So it would ease the mutualization of turbines for arrays. And we have a modular architecture composed with a steel structure, a steel foundation, ballast weights, and a turbine that can be removed one by one. So this is done for installation and reduce the cost of the installation. We will see that later. This is based on our experience. And we have a gravity-based support structure with ballast weight, which is good for environmental impact. Sabela work on a complete range from medium to high power devices because we want to adapt the rotor diameter depending on available water depth and rated power according to marine stream velocities. Sorry. Main advantages are that we want to standardize subpart to benefit the volume economy. Up to 25-meter diameter. We can adapt gravity-based or monopile foundation, and we can address a rated power from 2050 kilowatts up to 2 megawatts. Our main project actually is a D10 project, which is installed in Ocean Island. The 900 inhabitants, 4 tidal power gensets, and around 2 million liters of fuel per year consumed. The Sabelas project on this island is based in the Frontier Passage with a 55-meter deep, 2 kilometers off the shore, and up to 9 knots current velocity. This project was supported by French government and Brittany region. This is a 1 megawatt peak machine. In 2015, we deployed it in the Frontier Passage and connected to the electrical grid of Ocean, which is a weak and fragile off-grid network. And we operate and monitor the turbine during 12 months, the 12 months authorized period. So this is the machine. We have the height is around 70 meters and 20 meter large on the basement. The overall package is around 400 tons with a 10-meter diameter rotor, 1 megawatt peak power, and rotation speed from 5 to 15 RPMs. The first operation for this program was to install the export cable. We use a DP vessel, but without a dedicated crane. and we also use divers. And the installation strategy was made all in one. So we installed the foundation, turbine, ballast weight at the same time, and we use a standard heavy lift vessel equipped with two 450-ton cranes and maintained in position with 2 onshores and 3 tugs. The precision of positioning of the turbine was small flexibility in lat and long, and 3 degrees for orientation. The next operation was a connection to the grid, so we use a DP vessel also, but without crane, to recover the ILT on the seabed and to connect the jumper cable from the turbine to the export cable. And this was done in September 2015. On onshore, we have 2 containers, one for the monitoring of the machine and the other one for the security regarding the grid. After demonstration completion, the turbine was retrieved after 12 months authorized period, and we use a DP vessel, 400 tons capacity, and it was a success. We also test the reinstallation of the turbine on the basement. So we recover the turbine and we retry to put it on the basement, and it works perfectly. Because yes, the DP vessel has a great capacity of positioning. The environmental constraint we have in this kind of area are the complexity of operation, as we are in a strong current areas, and the assessment of feasibility and safety due to limited operation windows, because we have a limited number of nip tide. We have to work during a slack tide of nip tide, and these have a limited duration, around 1 hour and a half or 2 hours. And we have also the sea state and wind weather windows to be correct to operate. So this is a great limit to have an intervention on the machine. The feedbacks on the operation we made was first that the onshore vessels are not adapted for this operation. The vessel we used for the first installation was not able to maintain a position even with 3 tugs. And the improvement we applied for the following marine operations are first to choose an adapted vessel, a DP2 or DP3 vessel, with a station keeping capabilities up to 5 to 6 knots. We develop also adapted tools. We use a lasso to recover the turbine. The lasso is fixed on the crane of the boat. We built also a turbine offshore berth dedicated to offshore operation. And we also include a work rov on the DP vessel. We also work on effective method and procedures for the optimization of the operation with a detailed planning based on current velocity prediction, which is very important, and detailed procedure on clear tasks. So the use of adapted vessels is mandatory for tidal turbine, but not so many suitable vessels are available on the market today. The first problem we have is that the best vessel DP are limited to 5 to 6 knot station keeping, so we need to still operate during nip tides. After that, the best rov can hold station in current up to 2 knots. So during nip tides, this limit the work windows to slack tides, and the best DP vessel with high crane capacity are used in oil and gas industry. So we have expensive day rates and demob costs because the boats are not present on the area we work, and volatile price dependent on oil and gas markets. So the emerging needs to reduce the cost of marine operation, which are a large impact on the global cost of a tidal project. It's first a modular approach for installation to have to separate the turbine, yes, the basement, the ballast weight, made the installation in several packages to limit the package weight and to have lower lifting capacities needs for the DP vessels. We also need to reduce offshore operation duration so that we work on development of wet mate connectors so that we don't have cable handling during the operation, and development of adapted tools for material handling and positioning. This is to combine with modular installation, and this has to be worked with marine operators. And the aim also is to avoid the use of off-road, so to adapt positioning solution directly on the tools. And the next step, probably not today, but for array deployment and maintenance, would be to work on dedicated vessel on ROV for marine renewable energies, to have extended operational windows, to increase the site accessibility, to reduce downtime on related costs, and to reduce day rates. The final objective is to have a competitive LCOE for tidal. The main project we have, the first one is integrated inside the Tiger project. It is consists in installing 2,250 kilowatts machines, the procurement opportunity on that is the installation of 2 turbines and installation of 2 export cables. What we want to address in this project is to make innovation to reduce the weight of the package under 50 tons to address lower capacity crane vessels. The second step for this project, so for the first step, it would be installed in 2022 during the Tiger project. The second step is to add 18 machines on this first site to have a 20 machine array. For this one, we will have 2 subsea hubs to interconnect 10 machines. We have installation of 18 turbines and installation of 2 export cables. So we want to mutualize the export of the 20 machine on two export cables. The third step is to work on the second side inside the Gulf, Morbihan Gulf, and to add 20 tidal turbine on this site. With 2 subsea hub also on 2 export cables. And this is planned for 2030. The other project is a FAR project, which is a second step of Ocean project. The aim is to install 2 tidal turbines, but inside a global low carbon solution with the deployment of 2 tidal turbine, 1 wind turbine, solar panels, and energy storage capacity for a 20-year period operation. The procurement opportunity would be the installation of 2 tidal turbines, but this turbine would be more powerful with a 500 kilowatt nominal power and a 15-meter diameter, and also 2 export cables. So the total power of the clean energy would be 2.4 megawatts and will cover around 80% of the needs of the island. So that's all for me. Don't hesitate to ask questions if needed. I will let now Adam Leonard Williams from James Fisher present you Mermaids, their marine ops weather risk and optimization software. Thank you.
Thanks everyone for handing that over. And also thanks to the guys at EMEC and Monesto for inviting me to talk. So yes, my name is Adam Leonard Williams. I'm a marine ops consultant with James Fisher, and I work for the digital and data science team. So what I'd like to do this afternoon is just talk through our software, which is called Mermaid, which some of you may be familiar with. It's a piece of software that's been developed over the past sort of 7 or 8 years, and essentially allows you to create a digital twin of your marine operation and test it for weather downtime and allow you to kind of optimize your marine op. So we like to think that Mermaid is essentially, one of the market-leading softwares in this field, allowing you to model marine operations. And it comes from a very good kind of background, and it was designed by both marine engineers and naval architects. But it's actually been built by software engineers, and it's been tested, it's been validated, and it's been used across a wide range of the offshore industries, both wave and tidal, offshore oil and gas, and also hugely now in offshore wind. And a lot of this initial work was done by the guys at Mojo Maritime, and then James Fisher Marine Services. And essentially the idea is that we need a piece of software that allows us to model complex marine operations, not just the durations, but also the costs. And, we wanted to be able to simulate, groups of tasks with multiple dependencies, things happening in parallel, being able to group things together, repeating various tasks, etc., using multiple vessels, looking at the station keeping capabilities, looking at the site access, what ports can we use, how does the vessel transit, and wanting the flexibility to be able to test and compare multiple options. So you can do a lot of the testing of different ideas ahead of time, do it on the computer without making expensive mistakes later down the line. And also wanting essentially a one-stop piece of software for general met ocean assessment and site characterization. We've used it widely internally within James Fisher for feed studies. It's been used for installation and O&M studies, vessel and port selection, looking at general site statistics, creating, looking at different bids, and also looking at the insurance side of things. So Mermaid was kind of built and tested across a lot of the early tidal developments that Mojo and James Fisher were involved with. So some of these devices people will recognize already and have worked on themselves. So just to say that the software is not just a piece of academic work, it's being used and developed on the fly in the industry, and has got a very good reputation. And so what I'd like to do is just go through with you how the software kind of works, what it can allow you to do, and then give some examples of how it might be used in the future for developing arrays and what it might be used for. So the way it works is it's all a graphical user interface, so it's all nice draggy, droppy, clicky kind of stuff. So first thing you do is build a nice map of what you're doing and where it is, so your turbine locations, how you access your ports, and where you have met ocean data. The next thing you do is set up details of the vessels you're using. So in this case, it's offshore wind, but it could be anything. So, do you have jackups? Do you have multicats, CTVs, other support vessels? What are the vessels' transit speeds? What are their station keeping capabilities? Are there any site access limits that you need to consider? And any vessel costs that you want to model? And then you actually build this model of your operations. So this can be as complex or as simple as you like. So if you were just wanting a simple assessment of a couple of weather windows, you can do that. If you wanted to go down to the granularity of actually properly modeling a full storyboard operation, then you can, down to the last sort of 5 minutes, attaching something to a crane. It's up to you. And you can create really complex models if that's what you need to do. So things happening in parallel, various complex dependencies can all be built into it. And so once you built this model, what the software then does is essentially test it against long-term hindcast weather data. So the question you're asking is, if I've taken this operation, if I'd done it in the past 10, 15, 20, 30 years, how long would it have taken? And then on the back of that, the software will spit out a whole range of really, really useful results and intelligence that you can then use. So standard stats on durations, exceedances, Gantt charts, and all sorts. So what this then allows you to do is then maybe look at your results, go back into your initial model setup, reconfigure, change a vessel, change an idea for installation, rerun it, and then combine. Go through this loop a number of times, and ideally come up with some form of optimized model that you can then take forward in development. So I've just got a couple of brief examples of how it's been used in other industries. This is information, a model built for installation of a wave energy converting array. And this is used by a developer looking at installing both, in early stages of their technology readiness level, but then wanting to scale up to how do we install whole arrays, and what happens then from one device to maybe 10, 15 or 20. So we modeled, port operations, going offshore, doing the setting up the foundations, doing the cable lay and the installation, so that the full installation was modeled. And we came up with interesting results on durations. You can look at standard kind of box and whisker plots, and you can also look at statistics on, what are your timescales for reaching certain milestones within that deployment. We've used it for floating wind. We've looked at modeling installation of floating wind arrays. So looking again, modeling port operations, the impact of, what are the impact of towing to site, the modeling of the site arrival and setup tasks, etc., and then the hooking up of the device. And again, this was also similarly, what happens when we go from a single device up to 10, 20, 30 devices, because that's essentially what we're going to be having to look at. Is it might be straightforward-ish to do 1 or 2 devices, but what happens when things scale up? And again, offshore wind is now being used widely by a number of developers in modeling the entire installation campaign from the cabling to the survey, and in this case looking at foundations and piling. So modeling the sequence of 2 vessels, a heavy lift vessel and a barge, transiting offshore and onshore and back to base to reload, coming back offshore, and installing multiple foundations and doing the piling and grouting. So what I've done for this talk is built a relatively crude model of installing some devices off the north coast of France. You guys will be familiar with this. You have to excuse the fairly crude nature of it. I've kind of made up some of the stuff, but it's for illustration's purpose. So what I've done is I said, okay, I'm going to install 10 devices here, and I'm going to run with 2 vessels. One's going to be installing the foundations, and another's going to be installing the actual device. And initially, you're going to have the vessel can install just 1 foundation and 1 device at a time before having to return to port to reload. So you can see the map view within the software here, and how that's going to zoom in. You can see the vessel kind of transiting in and out of Les Adriaux. The storyboard kind of looks like this. So we've got the vessel doing the foundations is the red set of tasks, and the vessel doing the turbines is the blue set of tasks. So it's relatively straightforward. So the vessels each mobilize or reload and port. They transit offshore, connect to some moorings, and then lowers foundations, does an ROV survey, and then returns to port to reload. Meanwhile, the vessel with the device transits offshore, gets on site, rigs to a crane, positions the turbine, and then again an ROV survey to finish up with. And it does this loop 10 times to complete the array. Little bit more details about the kind of parameters and what I've done within the model. So typically the weather limits are ranging between 1.5 meters to 2 meters on HS. Current speed is between 0.5 meter and 1 meter per second, 0.8 meters per second. This is because the current data I've got is a little further away from the site, so it's a little lower than what you would actually expect, but it's in there to give the current speed impact, and a wind speed limit of about 10 to 14 meters per second, depending on the task. And we've got some fairly crude kind of tasks, and the duration between half an hour and 6 hours, but in reality, you break this down into much more detail and use it as a proper kind of storyboarding process. Certain tasks are kind of grouped together. So these tasks here are grouped together, so they must happen sequentially without any break. Likewise, the same with the ROV survey. Once you start this lot, you have to complete. And we've also put some marine warranties for air restrictions on some of these tasks. We're actually looking for a longer weather window than is actually required. A similar story with the device tasks. Positioning, overboarding, and then recovering, and then ROV survey, similar sets of limits, maybe some slightly lower ones on the tidal currents and wave heights. And so that's the model. And then we ran that over sort of 10 years, 10 years of historical hindcast data that I sourced from the guys at DHI. And what the Mermaid allows you to do is actually kind of interrogate that weather data, first of all. So you can look at time series of data. You can look at frequency tables and exceedance graphs. So you can get a good grasp of what the actual weather conditions are beyond just doing the model work itself. So you can get a good idea of what the ambient conditions are likely to be. So you can see actually here, this is quite useful. The current speeds, the data I've used here doesn't really exceed 1.5 meters per second. So it's a little low compared to what you'd expect on site, but that's because it's come from a slightly further offshore location. And so these are some of the results. So in this example, we can see that depending on the start month that you start the installation, your operation durations are going to range between somewhere between kind of 40 and potentially up to 140 days, depending on the month you start in and kind of the luck of the draw with the weather that particular year gets. So the box Muska plot presents a fairly basic set of kind of your minimum and max durations, your P25, your P75, and your P50. And you can see each individual marker is each individual simulation that the software undertook. So you can start to see the range and spread you could potentially get given the month you start in. You can look at a lot more detailed statistics on exceedances. So if you're interested in things like P90s, P10s, a different P value that you're particularly interested in, you can do that. And each of these lines is a different start month, so you can see the spread and range that you're likely to get. So for example, you can see your P90s in this case are ranging from sort of 52 days all the way up to beyond 100, 140. You can look at statistics on the timing at which you're going to reach certain milestones with an installation. So this shows you the time it would have taken to reach each individual turbine completed, and each line in this case is when you're starting in a different quarter. So if you were to start this operation between November and January, you can see how slow the operation takes as you go through turbine. Whereas if you go to start clearly late spring, early summer, you're going to be going a lot quicker stepping through. So you can use this to kind of gauge an idea of the speed at which you're going to go through each turbine. You can look at Gantt charts. So you can actually see how long each simulation took, how long each part of the process took, and you can see where the vessels are going, where the downtime occurred, and you can break that down into individual tasks. You can see, essentially where the vessels are transiting, where they're waiting. So you can really drill down into each simulation, see what happened, see where the downtime occurred. So that was the kind of the basic analysis, what I did. And I thought, well, let's show how you can use Mermaid just to do some basic scenario testing. So, try different ideas, different options. So what I've done is I have used Mermaid to say, well, actually, let's see what happens if we install just one device and what happens if we install 20 devices to see how those stats on duration scale up. I've also thought, well, let's just change the strategy on the vessels. So let's change the carrying capacity. So let's say the foundation vessel can carry 4 foundations, and actually the device vessel can actually carry 2. And then the third one I've done is actually just removing the current speed restrictions at all. So let's imagine a dream world where we've got a vessel that's capable of installing these things in any tidal condition. And then fourth one is actually combining steps 2 and 3. So I'll just go through this quite quickly. I'm aware of the time. Different number of devices. So the kind of the turquoise blue is the original 10 devices, and then orange is 20 and green is 1. So, as you'd expect, the durations increase with the increased number of turbines and such like. But what is quite interesting is seeing, especially between 10 and 20, is when the downtime starts to really kick in because of the weather, in that actually when you start looking at August and September, with just 10 turbines, you can kind of maybe get away with it. But with 20, if you start at that point, you're going to be looking at much longer durations because you're starting to run into the entire winter period for this. And actually for the one turbine, it's the spread is much less. So when you kind of look at the summary of just the P50s and the P90s, which is what this is, you can see the one device is fairly, it's a fairly straightforward set of durations in this respect, but the jump between the 10 and the 20 can be quite significant depending on when you start. I looked a little bit also at the ratios between the two. So yeah, an interesting feature here, the ratio of the P90 durations, when you go from installing one turbine to 10, yeah, and that's when you're suddenly taking in a lot of the winter rather than just a single device. So yeah, this can be a useful way of just using the software to gain intelligence on what's going to happen to durations once you start scaling up the number of devices. So the second thing I wanted to do was just look at what happens if we change the vessel carrying capability. So this is really easy done in the software. You can just select a task you want to look at, and then you can tell it to actually only do this resupply task on every 4th iteration. So instead of doing it every single time, it does every 4th. So the supply vessel stays offshore and goes on to each successive location to carry out the installation. We set it up so the foundation vessel does 4 foundations and the turbine vessel will do 2. And this makes, again, a significant impact on the statistics. So you can see that by doing that, by increasing your vessel capacity, you can bring your durations down quite significantly by, in some cases, 20 to 40 to 80 days, depending on which simulation we looked at. And again, looking at a summary of the P50s and the this is the P50s of the individual vessels. So one of the things that Mermaid allows you to do is look at statistics on vessel use. So you can see between each vessel, at the P50 level, we've dropped our utilization by 10 to 20 days, depending on the start month. So significant cost savings can be made by just looking at these kinds of things. So the third one I looked at was what happens if we remove the current speed restrictions. Slightly unrealistic, but you could read this as saying, what if we just increase the current speed limit on our vessel? So if we had a purpose-built vessel for tidal device installation that meant you could hold station in much stronger tides, this could be the kind of impact that you could potentially have. So we can see here that, again, compared to the original analysis, the durations dropped significantly. And again, here's a summary of the P50s and the P90s. So again, dropping your durations by anywhere between 20 to 40 days, possibly more, depending on what you're doing. And then finally, I combined all of those simulations. So what happens actually if we run it with no tidal speed characterization limits, and what happens if we run it with an increased vessel carrying capacity? And you can see here, you can use Mermaid to really nicely compare and contrast all these different options. So the light, the blue is the original model. Then we looked at doing it with the increased capacity, and that's with the tidal speed sort of limitation dropped. And then this is combined that lot. So you can just see how, as you go through this iteration of using the software to test and compare different options, you can, in a short amount of time, gain some really valuable intelligence about, where you can make some significant cost savings and where you can really, really gain kind of advantage and make things more efficient. So that's the end of my kind of whistle-stop tour of Mermaid, how it works and how it can be used in this kind of environment, in this field. And yeah, there's a dedicated website there you can go look at for more kind of videos, how-to articles, all that kind of jazz. Any questions, very happy to take them. So I'm going to stop sharing my screen now and hand back to Oisin. And yeah, thank you. I hope you found it interesting.
Perfect, thank you. Hopefully you can hear me. Thank you to all the presenters. Very interesting indeed. We've got some questions coming in thick and fast, and I think the first one is for the whole panel. So you can fight between you as to who wants to go first. I think some of you touched on this earlier, and if you've got any further comment, just chip in. You know, do we see a need for dedicated tidal energy vessels in the future, which are designed to cope with unique characteristics of tidal sites? Who wants to go first?
Yes, I will start to reply. As I said in my presentation, we see that actually we install only, I would say, small arrays, 2 or 3 machines, so it's difficult to have a dedicated vessel for that. The problem we have actually is that all the vessels we use are operating in North Sea, and we have a high mob, demob rate when we want to operate, and it's difficult to have a vessel for 2 or 3 days only, because they operate for more than 1 year for one project in oil and gas, so it's difficult. I think the first step is to try to develop some dedicated tools to adapt on standard vessels to lower the cost in the first approach, and work also on turbines. But on the next step, when we will have more bigger farms, yes, it would be to have dedicated vessels. So this with a big park, we can occupy for a large period a vessel on this park, and I think we can also mutualize the needs with offshore wind in the next future.
Okay, perfect. Thank you. Darren, do you want to say anything to add there?
Yeah, so I can see the benefit of having vessels that can maintain position in high-speed tidal sites. Maybe not for turbine installation, because there's only so fast a current that you're going to put a structure down into, but operations that require being on station for long periods of time, such as cable operations, so dry mating of cables, cable repairs. There's probably good opportunity for a vessel, a tidal specific vessel for those operations. And probably like anything, when the market needs one, it'll materialize.
Okay, thank you.
The guys at Mojo Maritime, James Fisher, did a lot of work on this several years back on trying to develop the HF4 vessel. Some of those guys might be online now, I'm not sure, but again, a lot of research is done showing huge benefit that we would give the industry with a dedicated vessel. But it was one of these horse and cart things. If you build the vessel, then the industry will use it, but they're waiting for the investment for the industry to build it. That seemed to be the big kind of stumbling block.
Okay, perfect. Thank you. Anyone else? Okay.
I was just going to add in, from our point of view, I think the most important thing is to optimize the time it takes to launch and recover the turbines, and then the type of vessel will emerge. But I think it's all about optimizing the time and then the cost of doing that launch and recovery. I don't think dedicated vessels will come until we have a full-time need to maintain a whole array of tidal turbines.
Perfect. Thank you. And while you're on there, David, this one here, are there opportunities for suppliers to work with Minesto across all their project portfolio to, I suppose, to provide a consistency in their operations throughout?
Yeah, the answer is yes, and I suppose one example is consenting, but there are a number of examples where we want to develop a specific expertise in doing something really, really well, and that expertise is not project specific, then we'd want to maintain that relationship across all the projects. And I think there's a number of occasions where that has been done.
Okay, thank you. Next question is, and I suppose again it's for the developers. And it came about during Erwan's presentation actually, so maybe he wants to go first. What mitigation was in place to address marine growth buildup, and what effect did marine growth have on performance, I suppose, if any? And also, was there any monitoring of underwater radiated noise? So, Erwan, do you want to go first on that one?
Yes. For the noise on the turbine, we have to address environmental assessment each time we have to install a machine. So we need to make a initial statement of the noise, and next with the machine. And the fact is, when you have one or two machines, there is the noise is very we cannot really hear it. Mostly if you have boat circulation on the area, so the noise of the machine is largely covered by the boats. For the marine growth, we work with on the coating, so that for the first implementation we use a hypothetic coating regarding the condition we have, and next we put some coupons on the turbine, and after that we use the best coupons on the next after the next maintenance, the following maintenance, and when we proceed like that. So the loss of performance is not so high because we adapt the coating to the different parts of the turbine.
Okay, perfect. Thank you. David, like to add anything there?
Yeah, we are also monitoring noise, both for the actual turbine itself and obviously listening for the behavior of marine mammals around our turbines. So that's an ongoing program which will support the industry, and a lot of work's been done already, but we're doing our share.
Okay, great, thank you. I have a question of my own, and it's to Darren actually. So from your experience, or you'll know from your experience, there are many sort of different solutions proposed to sort of capitalize on this marine energy resource. We have the different designs, the weights, operating principles, and so forth. Given that, where do you think the industry should sort of concentrate on when it comes to try and standardize different aspects of the industry? So, you know, if the turbines are so different, if the weights are so different, if the principles are so different, where do you think standardization should be sort of focused upon?
Well, I think the first thing to say is, you know, when you look at the project as a whole, you know, no matter what technology you're looking at, most things are actually the same. They've all got a substation, they've all got export cables, inter-array cables, they all need mobilization facilities. So there's actually already a lot of similarities across them. So I think, you know, as a starting point, the standardization should focus there. And that's a good area to collaborate on, which, I mean, it's part of the Tiger project. It's also been done very well in fixed offshore wind in the past. And we're seeing it in floating offshore wind as well, where developers are getting together, leveraging their investments by, you know, contributing into the same pot and making sure that for every euro you put in, you get, you know, that times the number of developers back out of it in research.
Okay, yeah, excellent. Yeah, good answer. Let's have a look. We've got some other questions coming in, but I'd like to go to Adam next, please. And just to sort of say, you know, we've all heard of sort of James Fisher, and you are, I'd say, an established practitioner, a very experienced marine operator in this case. I mean, given that, what aspects or of products and services that you kind of offer or on offer in marine operations sphere do you see as most sort of transferable to tidal stream energy, and probably where do you think the tidal stream energy industry should focus its development in offshore and onshore logistics in the future?
Okay, yeah, thanks. With regards to what Fishers can offer in this, I think is a range of things, because they have a lot of kind of independent smaller companies that form the group. So you've got parts of Fishers that specialise in the subsea work, so in the seabed preparation, the cable work, the survey, the protection side of things, the ROV surveys. You've also got the guys who are brilliant at the kind of the monitoring and integrity of devices and that kind of thing. But we're doing a lot of work now in the digital and data science side of things, so they're really pushing that. So looking at digital twins, looking at cable monitoring and using that to kind of try and really minimize downtime for these kind of structures. And that's been pushed more and more in offshore wind. I think with regards to your question on kind of logistics and how tidal can develop, I think they could do really well in looking at what's happening in floating offshore wind. So I think a lot of the similar questions are being answered and pushing from single devices to whole arrays, and not that dissimilar areas. So lots happening in the Celtic Sea at the minute, looking at mobilization bases, potentially long transits out to site. How do we do the O&M? Do we do an O&M on site? Do we tow back? So I think collaboration with offshore wind and especially floating wind could be a real benefit.
Okay, thank you very much. I think we've probably got time for one more question before we sort of close. I think it's quite appropriate, actually. So it is to all who want to comment upon. When it comes to timeframes from order to a delivery of a system, and I appreciate we'll all have slightly different answers here. So I'll start again. So when it comes to timeframes from order to delivery of system, how quickly can these systems be commissioned, and what are the particular challenges connected to speeding up this process? Who wants to go first?
That's a really big question. There's no simple answer to that. The components of the answer is obviously how different is the site to what the product is designed for. We're not in a position where we have sort of a range of standard products yet, so that will be one constraint. We haven't scaled up production, which is kind of the next step for nearly all of us. So we don't have that ability to turn a switch and produce 10 instead of 1. So I think the next few years are going to be very interesting from that point of view, because this is the next big test to the industry is how quickly can you go step up from a demonstration 1 or 2 turbines to an array of, say, 10 turbines. So not a fully convincing answer, but that's the components.
No, but good. It shows that there's still some work to do, and I suppose it sort of gives well, it shows us why what we're trying to deliver through Tiger is so important. Anybody else quickly? We've got a minute or so to go. Anybody else want to add anything?
I might just add in on top of that as well. I mean, in my experience, if somebody gets a purchase order for some technology, the lead time generally isn't actually just getting the kit built. It's undertaking the environmental assessments, the environmental surveys, financing the projects. So there's a lot more than just getting the technology built and onto a quayside somewhere.
Okay.
And I've seen that take years, I guess, in the past.
Okay, perfect. Thank you. I think we've run out of time, so I'll just sort of share my screen at the end here just to give you the sort of contact details. again for the OREC, who are leading on Tiger. I just want to thank everybody for attending. A special thank you to all the presenters, all the panelists for answering the questions and giving up their time. And thank you to EMEC and Carly, who's Carly, and Teo in the background for supporting. I'll see you in the next series, hopefully. Thank you very much. Bye.
Thanks, Ash.